If FAISS IVF feels unpredictable fast but low recall, or accurate but slow nlist and probe are the two knobs you must understand. Let's tune them and make the trade-off explicit. You might see a system that returns results in milliseconds but misses relevant items. Or you might see perfect neighbors but slow queries that cost you production latency. By the end of this video, you will know how nlist and nprobe change what FAISS scans, why that affects speed and recall, and how to pick sensible defaults you can tune later. I'm Professor Pi, teaching search and IR from basics to advanced with simple concepts-first Python that helps you solve bigger real-world problems. Context first. FAISS with IVF solves nearest neighbor search when exact search is too slow. It partitions vectors into coarse buckets, so queries only look at a few buckets instead of every vector. Engineers pick it when they need big speedups on datasets with thousands to millions of vectors, and when a small drop in recall is acceptable for faster response. Success looks like answering queries quickly while retrieving the most relevant items most of the time. The intuitive idea is simple. Nest controls how many buckets you create. More buckets means each bucket is smaller and more specific. nprobe controls how many of those buckets you open at query time. Probing more buckets raises recall, but costs more time. Imagine dividing a library into shelves. Nlist is how many shelves you create, and nprobe is how many shelves you glance through. We will build a small toy workflow to show the extremes. First, we make an exact baseline that checks every vector. Then we build an IVF index with a small probe. Then force a full probe. Then try a rule of thumb list count and a mid-range probe fraction. Finally, we evaluate batch recall. This makes the trade-off concrete before you tune for production. Now we build the exact baseline. This snippet builds an exact L2 baseline to anchor ANN comparisons. We seed NumPy for reproducible toy vectors and create X as 2,000 points in 16 dimensions. The variable flat is a brute force FAISS index flat L2 that stores all vectors without clustering. Adding X means future searches will compute distances to every vector, serving as the recall ground truth. Exact search is slow at scale, but guarantees perfect neighbors for evaluation later. The printed count confirms the baseline holds all points, which we will compare against IVF. Next, we make a basic IVF and probe only one list. This snippet creates an IVF flat index and shows the default probe fraction. The variable Q is a small perturbation of the first vector used to query the index. We construct IVF with nlist set to 32, which partitions the dataset into 32 coarse cells. After training, add inserts the data into those inverted lists, and nprobe equals 1 means only the single closest cell is searched. The printed value is nprobe divided by nlist, a proxy for work scanned. A small fraction is faster, but risks missing neighbors. Increasing nprobe increases recall and latency. Decreasing it speeds up but can hurt recall. Now we force the index to probe every list. This snippet sets nprobe to nlist to force full IVF scanning. We first get ground truth neighbors, GT, from the exact flat index for the same query Q. By setting ivf.nprobe equal to ivf.nlist, IVF probes every list, effectively scanning all vectors. We search with IVF and compute recall at 3 by intersecting I with GT for the first query. Full scan recovers exact results but removes the speed advantage, offering an upper bound on recall for this index. The printed recall and probe fraction show perfect recall and full probing. Next, we rebuild IVF using a rule of thumb for list count and pick a moderate probe fraction. This snippet rebuilds IVF with nlist about the square root of n and sets nprobe to 25% of lists. The rule of thumb for nlist helps balance memory and how coarse the quantizer is without manual trial. We use Index Factory to create an IVF flat with the computed list count, then train and add the data. The nprobe choice of 1/4 of nlist targets a mid-range speed recall point, often a solid starting default. Larger nlist increases partition granularity and may reduce candidates per list, while keeping the same probe fraction steadies work per query. The printed values confirm the new nlist, the chosen nprobe, and the probe fraction relative to the total lists. Now we measure batch recall with a full probe baseline to confirm correctness. This snippet evaluates batch recall at 3 using a reliable full probe baseline. We create 10 slightly perturbed queries and get ground truth from the exact flat index. Setting IVF nprobe to IVF nlist probes all cells, ensuring IVF flat matches exact results for a fair baseline. We then compute mean recall across the batch by intersecting approximate and exact top 3 per query. Use this as a sanity check before dialing nprobe down to trade recall for speed. The printed numbers show perfect recall and the full probe fraction, validating correctness. Mapping this toy example to a real system is straightforward. If your data set is larger, increase nlist to keep buckets small, but also increase nprobe when you need higher recall and can afford extra search time. Measure latency per query and recall over a held-out set. Use the exact flat baseline on a small sample to get reliable ground truth. Recap: nlist is how many buckets you build. nprobe is how many you search. Use more nlist for finer partitioning and more nprobe to recover missed neighbors. Caveat: probing every list gets exact results but costs the same time as brute force. Next step: tune nprobe while holding nlist fixed to find the lowest latency that gives acceptable recall for your application. If short practical IR helps, subscribe and watch the IR videos.